All right, so we're in the chapter on chemical equilibrium, and near the end, not today, tomorrow or the next time we meet, we'll talk about phase equilibrium. These are the big equations. We have a reaction equation or a dissociation equation for reaction. It can proceed in the forward direction as well as in the backward direction. At equilibrium, some of the A and B are being consumed to produce C and D, but some of the C and D are being consumed to produce A and B, and then there's kinetics going on a molecular level, but for the overall system, the amounts of A, B, C, and D are constant with time. We talked about the Gibbs free energy, and it was a long and tedious derivation, but you get a relationship where change in the Gibbs function for the reaction, you can put it onto this side of the reaction equation or equilibrium equation. You can separate out temperature-dependent components on the left-hand side, and then the composition, the mole fractions, and equilibrium plus pressure-dependent, if it is pressure-dependent, on the right-hand side. They introduce K. Oh, I forgot the name of K. What is K? K is the equilibrium constant for that reaction. The log of K is defined as this, so K is the exponential of that. And then you have two forms of the equilibrium equation. So you have the equilibrium constant, function of temperature, is equal to either in terms of Y's, mole fractions, and pressure, stoichiometric coefficients. This is one form, or the equivalent form, if you wanted to work with not mole fractions, but the total amount, N, then the total amounts are given. This is the same equilibrium constant K. Where do we get those equilibrium constant Ks? We only have a few reaction equations in this textbook. So if you count, just say reaction 1, 2, 3, 4, 5, 6, 7, 8. That's it. There's many more reaction equations out there. It's just that there's only 8 tabulated for the equilibrium constant K. And so what they report is log base 10 of K. So you come down as a function of temperature. Maybe you go to 3000 Kelvin. Maybe you're interested in studying or analyzing this reaction equation. And so the coefficient, the log base 10 of K is negative 0.485, hence K is 10 to the minus 0.485. It's a function of temperature for the equilibrium constant. Let's solve this problem. We have 2 kilomoles of carbon. It reacts with 3 kilomoles of oxygen to form an equilibrium ideal gas mixture of carbon dioxide, carbon monoxide, and oxygen. And they tell us the temperature, 3000 Kelvin, and they tell us the pressure, 3 atm. So as a reminder, we're going to try to identify the appropriate reaction equation. There's one of 8, so to speak, to pick from in this textbook. And we'll use the equilibrium equation. At equilibrium, that's how the components are related to each other. Okay. So let me back up a little bit. Let's say I have a reactor where I'm feeding it some carbon. I'm also feeding it some oxygen. What comes out of the reactor? Well, it's a mixture of carbon dioxide, carbon monoxide, and oxygen. You have to read the problem carefully. Does it say anything else that exists in this ideal gas mixture that's in equilibrium? This is in equilibrium right here. What comes out? Oh, we didn't say what went in, it was in equilibrium. It's just after the reaction equation, what comes out is a mixture that's in equilibrium. All right? Did it say anything else? Maybe, how about this? Is there any N2? There's no N2. There's no N2, okay? Is there anything else exotic, like, I don't know, C2O2, make stuff up? No. Just got 3 components, that's it. So in the problem statement, it tells you these are the 3. So what you want to do is you want to say, I want to find the appropriate reaction equation that would link in these 3 components in equilibrium. Let's go back and take a look. Which of them? It's the 7th one, isn't it? It's CO2 dissociates to carbon monoxide plus 1/2 O2. So if I write it like this, CO2 dissociates to carbon monoxide and oxygen. There's a 1/2 there, there's a 1 there, and there's a 1 there. And so you start to say, anytime I see a nuse of A, it's 1. The A is carbon dioxide. Anytime I see a nuse of B, it's 0, and there isn't any B. Anytime I see a nuse of C, the coefficient's 1. And anytime I see, I know it's a little confusing, but C is for carbon monoxide. The 3rd entry in this reaction equation is carbon monoxide. And then anytime I see a nuse of D, it's a 1/2, and D is for my O2. Make sense? Is there any carbon in the output? There isn't any. They told us that, so don't worry about it. Okay? So one of the equations that we'll have is we'll have the application of this equilibrium equation. So let's go ahead and figure out that the K is equal to the power negative 0.485. That's for this reaction right here at 3,000 Kelvin. Go back to the table. This is the reaction we're studying, the dissociation of carbon dioxide. And at 3,000 Kelvin, this is our log base 10 of K, hence K is 10 to the power negative 0.485. So that's the start of this equation. The left-hand side of that equation is 10 to the minus 0.485. So let me leave it symbolically. K is equal to, now I have to have the amount of, that's N of C is the amount of my 3rd component. That's the amount of carbon monoxide raised to what stoichiometric power? 1. Then it's this one. It's the amount of oxygen, true, raised to what stoichiometric power? 1/2. Divided by, then we're going to do this one, the amount of carbon dioxide raised to what power? 1. And then forget it, there's nothing raised to the 0th power is 1. So it's just multiplied by 1, okay? Don't, this right here, when it's not there, is 1. Okay, it's not dividing by 0, it's just multiplying, dividing by 1. Okay, let's finish this out. We'll have the pressure of the mixture. Notice the pressure of the mixture is 3 atm divided by P ref. What is this P ref right here? It's our reference pressure. Numerically, what value is it? 1 atm. 1 atm, that's right. Okay, then we divide by the total number of moles in the mixture. Well, would that be the number of moles of CO2 plus the number of moles of CO plus the number of moles of O2? Is that N? Is that the total number of moles of my mixture? I only have 3 components in the mixture. And then I raise it to the power. What's nus of C? 1. What's nus of D? 1/2. What's nus of A? Minus 1. What's nus of B? Minus 0. So just leave it off. So you have to be able to map the generic case to the actual case that we have. We're studying this, the dissociation of carbon dioxide. That's one equation. What are the unknowns? Well, you want to calculate the equilibrium composition of the gas mixture. You want to calculate how many moles of carbon dioxide there are, how many moles of carbon monoxide, and how many moles of oxygen there are. That's one way of expressing the answer. So I have three things I'm trying to calculate. I have one equation, three unknowns. Mathematically, what do you think? One equation, three unknowns? Nope. You have to go get more equations, right? We'd like to get the same number of equations as there are unknowns mathematically. It's just one of those principles in mathematics. I want two more equations. The first equation is a statement about the equilibrium constraint. What's the other one? They're going to be a balance equation. Balance of what? What do you think is absolutely guaranteed to be conserved? Yeah, but when you break it down in study of chemistry like this, we are conserving, and there's going to be two of them. There's going to be a balance of this and a balance of that. Balance of carbon and a balance of oxygen. Is there any hydrogen? No. Is there any nitrogen? No. Is there anything like argon? No. Chlorine? No. It's just carbon and oxygen, that's it. So when you have a balance, you have an in, whatever comes in must equal to out. So go back to this illustration. How many kilomoles of carbon came in? 2 kilomoles went into the reactor. So 2 is the in for the carbon balance. Now, I don't know how many kilomoles of CO2 went out. That's an unknown. I'm trying to solve for it. But for every kilomole of CO2 that comes out, how many kilomoles of C are in it? 1, 2, and 3. I heard all of them. Just count. If I have 1 kilomole of CO2, that means there's, for every mole of CO2, I have 1 of C and 2 of oxygen. So I only have 1 right there. Next one, I have the number of moles of carbon monoxide. I don't know that. I'm trying to solve for that. Let's say it's a half a kilomole or 5 kilomoles, whatever it is. How many moles of carbon go with every mole of carbon monoxide? 1. This one's probably the hardest one. I have so many kilomoles of oxygen going out. For every one of those kilomoles of oxygen, how many kilomoles of carbon do I have with it? 0. Now read this very carefully and write the oxygen balance equation. I'm going to pause. I'm going to walk around. I'm going to see you do it, okay? I want you to write the oxygen balance equation. Balance O's. Don't balance O2's. You'll be tempted. Some students are tempted to balance O2's. Balance oxygen O's. Thank you. All right. Well, the N's for the oxygen. Balancing O's, not O2's. If I have 3 kilomole of O2 coming in, how many kilomoles of O go in? 6. Now, we have the number of moles of CO2, right? Look at CO2. It's 3 things made up in there, right? One's a carbon, one's an oxygen, one's an oxygen. That's CO2. The subscript 2 is not on the carbon, the subscript 2 is on the oxygen, true? So if you looked at it, it'd be like a carbon, oxygen, oxygen, something like that, floating around. I think it looks more like this. Carbon, oxygen, oxygen. I think it looks like that. I don't think it has a what do they call that? A dipole. All right, so how many oxygen for every CO2? 2. Now, I have so many COs coming in. And how many, I'm going to let you finish it out. I want perfection from you. Got it? So I have 2 blanks. Fix it. All right, maybe I should have written it up here. I can put the 2 kilomoles of carbon are coming in. And I can put the 3 O2s coming in, right? And that's how you're able to get this 2 in the carbon balance and that 6 on the oxygen balance, right? Going out, I don't know how many CO2s. That's an unknown. It's the unknown N CO2. I don't know how many COs. I know I have some CO going out, but it's unknown amount of CO, and I don't know how many O2s are going out. That's what this represents, this number of O2s going out. Can I say it's 5? Can I say it's 18? Can I say it's 2? Can I say it's a half? I don't know. But once I know this, it'll be certain, like 0.32467 kilomoles. Well, if there's 0.34, whatever, 67 kilomoles of O2 going out, how many O's go with it? 2 times that. 2 times that. So what's this coefficient go right here? 2. What's the coefficient go here? 1. Almost too easy, isn't it? Well, I have now an equation. I have an equation with unknown. Right? Let me kind of clean this up a little bit. Clean it up, clean it up, clean it up here. 1, 2, get rid of this underline. That's a 2. All right, let's count our equations. I have this equation, our first equation. I have a second equation and a third equation. Where are the unknowns in the equation? These is the unknowns. I have 3 equations, 3 unknowns. Now, mathematically, how am I going to solve it? You've taken more mathematics classes than you can choke on in your lifetime. Think about all that elementary school, all that middle school. Every year you had a math class. Every year of high school, math, math, math. College, oh, you want to be an engineer? Let's see if you can make it through Cal 1, then Cal 2, then on, right? Come on now. This should be within our purview. 3 equations, 3 unknowns. How are we going to solve for it? Well, one of the strategies is to eliminate some of the unknowns and get 1 equation and 1 unknown. You don't have to, but that's usually one of the given strategies, right? Let's do this. Instead of using this as a symbol of unknown, let's say this Z is going to be my unknown. I'm going to solve for Z. I know I could use X, but I think the book uses Z. And Z is the number of moles of carbon monoxide. I just picked that. Taking one of these equations, this equation right here, and rewriting it where every time I see number of moles of carbon monoxide, I put Z. So I'll have 2 is equal to the number of moles of carbon dioxide plus 1 times Z. You know what? Anytime now I see the number of moles of carbon dioxide, I can replace it by 2 minus Z. Anytime I see the number of moles of carbon dioxide, I replace it by 2 minus Z, right? Take this equation. Anytime I see number of moles of CO, replace it by Z. Anytime I see the number of moles of CO2, I replace it by 2 minus Z, and I'll get an equation for the number of moles of O2 in terms of Z. Can you do that? I'm going to pause and I'm going to see if you can do that. All right. So a number of you were able to work it out where you get the number of moles of O2. Come on, write it down. The number of moles of O2 is equal to 1 plus Z divided by 2, correct? You got to be able to do that, okay? Now, I have used this equation, I have used this equation, What was I able to get out of it? I was able to get this result out of the first equation. I was able to get that the number of moles of O2 is equal to 1 plus Z divided by 2 from the second equation. This was a definition. That's my primary unknown now. Now I go back to the equilibrium equation and I just rewrite it. I rewrite it like this. I say, K is equal to the number of moles of CO. That's Z. Times the square root, that's the number of moles of O2, take the square root of that. That's 1 plus Z divided by 2. And you have divided by the number of moles of CO2, which is 2 minus Z. All pressure, 3 divided by 1. The reference pressure is 1. And then you have to sum these up, right? When you sum them up, the number of moles of CO plus the number of moles of CO2 plus the number of moles of O2, that's going to be Z plus 2 minus Z plus 1 plus Z over 2. So these Z's cancel, and you're left with the sum is equal to 3 plus Z divided by 2. Did I do that correct? Do you agree? So it's 3 plus Z divided by 2. Now, we go and we have to do this exponent. We already did it up here. The 1's cancel. And so we're left with an exponent of 1/2. True? 1/2. Did you see what we did? Had 3 equations, 3 unknowns. Equilibrium, oxygen balance, carbon balance. I wanted to get 1 equation with 1 unknown. Now at this point, I want to solve this problem. The K, I know what that is. That's 10 to the minus 0.485. Can you see it's 1 equation with 1 unknown? How are you going to solve for that? This is why you're allowed a calculator on the exam. But guess what? You have to know how to use your calculator. So, how many people can program their calculator to do a function? Every one of the calculators on the approved list can do it. You can program up a function, then feed it a value, feed it a value, feed it a value, right? You can do that. Probably the best one that's on the approved calculator list is the Casio. That's what people have told me. But the TI can do it too. There's a little pamphlet that comes with your calculator. Pull it out and read it. Got it? Be prepared to do this on the exam. But what you got to do is you got to code up a function. Let me try and draw it like this. You want to code up a function of Z. That function of Z will be the K, 10 to the minus 0.485 minus Z square root 1 plus Z over 2 divided by 2 minus Z 3 over 3 plus Z over 2 to the power 1/2. See, that's a function of Z. And you just make a little table. You say, there's my guess of Z. Maybe I guess 0.3. I run that to see if it's equal to 0. Does it solve that equation? The equation comes in at 0.143. It's not the solution. I'm doing it by hand. So I guess another value. Guess 1.0 for Z. It comes in at negative 0.807. The value of Z is between 0.3 and 1. Can you see that? It changed sign. It went from something that's positive to something that's negative. Do a linear interpolation between these two values to get a next best estimate. That's easy. The next best estimate should be around 0.41. When you evaluate it, 0.0053. Probably on the exam you could stop there. You've shown what you're doing. But if you want to do another one, do a linear interpolation between these two values. You'll get an updated 0.47, negative 0.001. Do one more interpolation, 0.4685, 0.0000. You're there. If you have a calculator, often you can code it up, give it a guess, and let it run as a root finding, and you'll solve for it. If you wanted to plot it, you're trying to find the z where the function goes through 0. Root finding, that's all it is. All right. So there's the solution. Once you have z, you come back up here, and now you can interpret it. Oh, the number of moles of carbon monoxide in the equilibrium mixture, that's 0.4685. The number of moles of CO2 in the mixture, you just use that equation, 1.5315. And then the number of moles, I'm going to put kilomole. And then the number of moles of O2 is 1.234 kilomole. Those amounts satisfy all three equations. They satisfy the carbon balance, the oxygen balance, and the equilibrium equation. Ready to press forward? Sometimes you'll have a problem where there's quote-unquote an inert gas or inert component going for the ride. For example, last time we just talked about carbon coming into a reactor, and we brought in oxygen into the reactor, and we went out with carbon dioxide in equilibrium with carbon monoxide and oxygen. True? What would somebody do if they said, nitrogen goes along with oxygen? I don't have a pure stream of oxygen. I'm getting oxygen from air. Well, somebody could say that I'm not going to model the dissociation of nitrogen. I'm going to neglect that. Basically, nitrogen would act as an inert component. You say, couldn't nitrogen dissociate? Sure it could. Well, then switch it to argon. Argon's not going to dissociate. Okay? It likes it by itself. Noble gas, right? But that's pretty unrealistic. It's more realistic if it's something like nitrogen that doesn't dissociate. Well, let's go ahead and write down our equation again that we had. We had CO2 goes to CO plus 1/2 O2. Isn't that what we studied to help determine the equilibrium composition? And then if we look at the equilibrium equation, we had K is equal to the number of moles of CO, the number of moles of O2 to the 1/2 power, the number of moles of CO2. We had some pressure over the reference pressure, and then we had the total number of moles. But now it changes because the total number of moles is not only the amount of CO and the amount of O2 and the amount of CO2, it also includes the amount of N2 because it's part of the equilibrium mixture going out. So you have to include it in that equation. That's where you include it right here. How about the exponent? So it's still 1/2. Let's change it up a little bit. Let's say I'm bringing in some methane. Let's say I'm bringing in oxygen, right? And what comes out is the equilibrium mixture of carbon dioxide and water, but it also could have some carbon monoxide and some H2. That's our last reaction equation, this one right here. Take a look at that one. Carbon dioxide, hydrogen, carbon monoxide, and water. So that would go out in equilibrium. What happens if I have nitrogen going along? I put the nitrogen right there. Or if you're afraid it might dissociate, call it argon. Call it an inert gas. Let's take a look at the equation. We'd have a K, equilibrium constant. We'd have the number of moles. First, I have to write down the equation for the reaction. The equation for reaction is CO2 plus H2 goes to CO plus H2O. And all those coefficients are 1, 1, 1, 1. There's no 1/2 power or anything for the stoichiometric coefficient. So we have the number of moles of CO to the 1 power, the number of moles of H2O to the 1 power, the number of moles of CO2 to the 1 power, the number of moles of hydrogen to the 1 power, the actual pressure divided by the reference pressure, and the sum of the n's. That's the sum of the CO2 and the amount of CO and the amount of H2O and the amount of H2 and the amount of N2, right? That amount of N2 is what is, if you have an inert gas, needs to be, that's the only place it comes in. But what about this, this coefficient? It's 1 plus 1 minus 1 minus 1, isn't it? So if it's that, does this cancel? So it's all to the 0 power. So if it's all to the 0 power, all of this is 1. And the amount of N2, the inert gas component, doesn't matter. It doesn't play an effect. When this coefficient's 0, when the coefficient's a half, the amount of N2 plays into it. Actually, this also says the pressure doesn't affect it. The pressure doesn't affect the balance, the equilibrium balance. So it could come out 3 ATMs or 1 ATM and it wouldn't make a difference. I have just enough time to set up a problem. Methane burns with 90% theoretical air to form an equilibrium mixture of CO2, CO, H2O, H2, and N2. So these are those 4 components we just talked about, and they are in a reaction equation together. And N2 goes out by itself, no NO or anything else, or it just is N2, so it's not going to disassociate. We're not modeling that. So what you'd have to do is you say to yourself, okay, the chemical reaction or equilibrium equation that I'm going to consider is CO2 plus H2 in equilibrium with CO and H2O. I'll put that to the side. But I come back here and I say, methane burns with 90% theoretical air. So let's go ahead and write down a balanced equation for 100% theoretical air and the combustion of methane. CH4 plus, I'm going to get the oxygen from the air. It goes to how many carbon dioxides? 1. How many water vapors? 2. So I go back and I rebalance to finish the oxygen. 2. And then I finish the nitrogen, 2 times 3.76 N2s. Leave that equation alone once you got it right for 100% theoretical air. True? Now write it for 90% air. See, this is our problem. 90% theoretical air. So it's CH4. Don't go changing the fuel. Leave the 1 in front of the fuel, right? Anytime you're tempted to change the coefficient, there, don't do it. And then what do we do? 0.9 times 2 times O2 plus 3.76 N2. Is that correct or not correct? That's correct. And we don't know how many CO2s come out. We don't know how many carbon monoxides come out. We don't know how many H2Os come out. We don't know how many H2s come out. And there isn't going to be any O2s coming out, but we will have some N2s going out. Right? This coefficient from the N2 I can do right now, because nitrogen doesn't participate, it just goes for the ride. So that coefficient is 0.9 times 2 times 3.76. We want to solve for the amount of CO2 that comes out. We want to solve for the amount of CO that comes out. We want to solve for the amount of H2O that comes out. And we want to solve for the amount of N2 that comes out. 4 unknowns. 4 unknowns. One equation I'm going to get from equilibrium from this reaction equation. It's going to look something like, if I can tuck it in over here, it's going to look something like K, the equilibrium constant, evaluated at that temperature, is equal to the number of moles of CO, number of moles of H2O, divided by the number of moles of CO2 and the number of moles of H2. Then I'm going to have the P over P ref. Then I'm going to have N total. But you know what that exponent up there is going to be? 0. So it's like I can just forget about that whole term. It's 1. And so K is equal to just the ratio of the N's, like I'm showing right there. That's one equation. Where does it come from? Equilibrium. Where's the other 3 equations come? Balance equations. Balance. I need to balance carbon. I need to balance what else? Oxygen. And I need to balance hydrogen. You got the pattern. Got it? I'm going to stop there and we'll pick it up here next time. Thank you.